Hey guys, welcome to NumPy for data science. This is going to be a full course. NumPy is really useful. It's useful and in conjunction with other packages in Python like matplotlib and scikit-learn, which is a machine learning package. So it's useful in many practical cases. Now, today I'm going to be discussing probably everything you would need to know for data science. Okay, so NumPy arrays and manipulation, indexing and slicing, dates, vectorized operations, universal functions, performance optimization, linear algebra, sequences, random number generation, working with missing data, building graphs, and machine learning applications. So let's begin. NumPy array is basically the building block of a NumPy array is using that NP array function. Now we've got this one-dimensional array, and then we got a two-dimensional array. Okay, so the two-dimensional array will have some kind of matrix form, and this is basically, I mean, you can consider it like a list almost, right, in Python. Now, in order to get the shape of this, we would use this dot shape function, and then we could see that it goes for the matrix, it'd be 2 rows and 3 columns. Now, this list here would be considered a row. This list here would be considered a row, but the elements inside of it would make up columns. Okay, so those are 3 columns for each. Here's another example, X, and we see we've got 10 rows and 2 columns. Now the matrix type, data type, which is D type here, it's an integer, okay? And then the size we could see for X is 20. The number of dimensions for the matrix is 2, okay? 2 rows, 3 columns. I mean, if we put, let's make it a little bit more consistent here. We would say it's 6 elements and 2 dimensions, okay, for the original matrix. And if we count them up, obviously it's 6. Here's something with view and copy behavior. Like if you want to take a subset, basically, okay, and then just look at a subset of it, we take 5 elements and then we do this dot view here, okay? Here's the thing though about this though, is that here's the thing about this though, is that if you change an element in the view, okay, it's going to change the original data set. So like if you see this negative subset 0, -1, where we take the first element and then we replace it with a -1, it'll change the view, subset view here, but it'll also change the large data here. So that's something to be aware of. If you want to take a subset of your data and basically work on it and not have your original data tampered with, you could do a copy, and that would be a much safer view, safer way of doing things. Okay. Um, Here we do it, we replace the second element with 88. Okay. So the copied array will change it to 88. Okay. But it won't change the original array, whereas the view did, right? The 99. It changed the original array. Okay. So that's the difference between copy and view. Okay. If you want to isolate a particular data set and not have it tampered with, that's what you would want to do is use copy. Here's a 3D array. Okay, so a 3D array has the way to look at it is 2, 3, and 4 is like there's 2 matrices. Okay, I would put it that way. Then there's 3 rows, which was the list which we saw in the two-dimensional view, two-dimensional array, right? 3 rows, and then 4 columns, which is the number of elements. Okay, so the number of dimensions is 3. Going on to H stack and V stack. These are two ways to concatenate data sets. You could concatenate it. I would say columns, adding columns here, right? And then adding rows, okay? So the H stack, you're adding columns, okay? And then the V stack, you're adding rows. Here we see something like where we have a temp, okay? So the original temp, okay, is this row here, these two rows, okay? And then we're stacking 2 times temp to it, okay? With the V stack, okay, now we're putting rows on it, right? So we have 1, 2, 3, 4, 5, 6. Now we're adding 2 rows, okay, 2 extra rows. So we're adding columns, okay? 1, 2, 3. 2 times temp is 2, 4, 6, okay? Temp, 4, 5, 6, 8, 10, 12. Remember, the elements are column-wise, and the brackets are row-wise. So we have temp here. We have 1, 2, 3, 4, 5, 6, those 2 rows, right? Then we're multiplying it, 2, 4, 6, and 2 times 4, which is 8, 2 times 5, which is 10, 2 times 6, which is 12. So we end up with 4 rows. That's the V stack. So here's array indexing and slicing. And the important thing to note is the position, okay? Along axis 0, you see 0, 1, 2, and then along axis 1, 0, 1, 2. Now these are the positions, right? So here's a row-wise, it'd be 0. Column-wise, it'd be 0. Row-wise, it would be 0. Column-wise, it would be 1, 2, okay? And so forth for each of these positions. Now, if we take 1, 2 for this array, okay, we get the position 6. Now, looking at this, what will we do? So this is the row, but we know it's indexed by 0. So 0, and this is 1, okay? Now, we're here at 1 in this list, 4, 5, 6. The positions of the column is indexed by 0, 1, and 2. So 1, 2 would be 6, and that's what we get here. Here's a simpler array. 2, 5, we get 0, 1, 2. So it would start at 2, and it would end at 4, right? Because 4 is actually 5. The 5 is the index value, okay? Now, if we were to get a sequence, okay, from 1 to 8, and the step size is 2, we would do 1, 3, 5, and then 7, okay? So that's something that's very important to keep in mind, that when we say 7, when we say 8 in the index, we're actually meaning the 7th value because of this 0. The 8th value here, which is 7, okay? So don't confuse the index value and the actual value is what I guess I'm trying to get at. Here's a Boolean, and a Boolean is basically a true or false statement, okay? So if an array is greater than 10 in this array here, it'll assign a true, okay? So 12 is true and 15 is true. Everything else is false. Okay, so it'll output 12 and 15 when we run it. Now, if I said, if I gave you this array and I said anything greater than 10, what would I give? So if you look at it element by element, you can see that basically 12, 13, and 14, I'm sorry, 11, 12, 13, and 14 are all true because they're all greater than 10. And that's how it would come out as a Boolean value here. Now, if I wanted to get the actual values that are greater than 10, I would have to put this temp greater than 10, okay, in brackets, and then temp here. So this would be the subset of the original data set temp. And I would get 11, 12, 13, and 14. Now we're going to be talking about dates. In order to create a range of dates, basically we could use this .arange function, and we would give the start of the date and the end of the date, and we could put it in strings, okay? And the data type would datetime 64D, okay? And these are generated dates, okay, that we could use. Pandas has an equivalent function. I mean, it's going to be ultimately when you do some type of data analysis up to you as to what you use. I mean, preferably if you're using a lot of pandas, you'd want to use pandas date range or whatnot. But this is a NumPy option. Now we could add like say 5 days to a date, right? So we use this np.datetime64. We give the date and this time delta function of 5, and then the D represents days. Okay, we could use like months and weeks and whatnot, but I've chosen to use days. And we see that from 2021 0101, 5 days later, it's the 6th. Now here's the example of time difference. Basically, these are time differences between 2 months. Okay, and we could just subtract and then get 31 days. Here's vectorized operations, and I'm going to be discussing a couple of functions. Well, not a couple, let's say a lot of functions here. Starting with a where statement, there are going to be times when you're going to need to subset your data, okay? And the where function is very useful. And you're going to want to either maybe convert values to 1, 0. Like an example would be like an indicator function, where things like yes or no or binary type of values are important, like yes or no, succeed or failed. I mean, these are variables that you could add to a linear regression model, to a machine learning model or whatnot, right? So where is it useful in the sense that it creates numerical values even out of text values too. But in this case, in this example, I'm subsetting the data. Something that's greater than 25, I assign a 1. Something that's less than 25, I would assign a 0. And you could see that 30, 40, 50 is assigned to 1s, okay? Reshape and transpose, these are pretty two important things. Going back to our 1D and our 2D array, we see that the shape for the matrix was 2, 2, 3. Now I could reshape that 2 by 3 matrix into a 5 by 1. And how I would do it is basically put the 5 and then the 1. Okay, so just change the dimensions after I put this reshape function. So it'd be 5 rows. Remember, the brackets designate rows, while the elements within the brackets designate a column. So there's one column, okay? And then I could transpose this. Well, I'm not going to transpose the reshape, but I'm going to transpose the original matrix, which is a 2 by 3. And it's going to turn into a 3 by 2. So 3 rows and 2 columns, one element within each column. Now I could also resize it. Okay. And we could see that this temp shape is 2, 3. 2 rows, 3 columns. Okay. Here are two good functions as well, ravel and flatten. Okay. So here you could see that we've got 2 rows, 3 columns. Okay, we apply the ravel function. Okay. And then the output we get is 1, 2, 3, 4, 5, 6. So it's basically collapsed into 6 rows. Okay. And then we could change one of the elements into 99. And that's what we do. So now we do a flatten, which does basically the same thing. Okay. And now we try to modify the flatten. Okay, but it doesn't change it. Okay. I should have run this, sorry. Here, here. Okay, so this does not change. We can't modify the flat. So here we could flatten row by row with C. And then we could flatten column by column. So here's an example that you would use the ravel function in image processing. A 3 by 3 array, you might want to flatten it into a 1D array. Okay, and so in order to do that, you would use this dot ravel. And it's useful in machine learning because this flattened array is an input into like a model, like neural networks, for example. Flattening like 28 by 28 pixel images into, a 1D array for neural networks. Okay, so that's an example and a use case. And moving on to attraction, I mean, arithmetic, subtraction, multiplication, and division. Now, these are vectorized operations, obviously. Now we could just basically do this. Okay, so we add, okay, 1 plus 4, 2 plus 5, 3 plus 6, A minus B, we get -3, and so forth. We multiply it out, right? Multiplying two arrays, and same thing for division. We could use NP vectorize, right? And it's used to apply a scalar function to an array element-wise in a vectorized manner. Okay, so we've got this array here, and we've got this custom function. We could apply this custom function to each element. So element-wise, right? And when we do that, we basically get 4, 9, 16, 25, and 36. Doing the first one, we do 1 to the second power plus 2 times 1 plus 1. So it's 4. 2 times, it's 1 to the second, right, which is 1, plus 2 times 1, which is 2, plus, which is 3, plus 1, which is 4. Okay, and we apply that for each element. Here's an example of something called broadcasting, and this is very powerful. It allows you to perform operations between arrays of different shapes and sizes. So we saw that with the addition. Now, if we add four, 1, 2, 3, right? 3 columns to 1 column, we could do that. And it's as simple as that. It's 4 plus 1 plus 2 plus 3. We get 5, 6, 7. Now you see the different dimensions here. We could also multiply, right? You see that these are uneven, basically, okay? And it's going to multiply 4 times 8 times 12, 4 times 4, 4 times 5, 4 times 6, which is 16, 20, and 24. Now we could add 1, 2, 3 to 1, 2, 3, and then 4, 5, 6, and that's what we get. We get 2, 4, 6, 5, 7, 9. Sorting is something that's extremely important. I mean, you're going to use this in data analysis, I would say pretty frequently, so it's a useful function. Basically, if you want to sort an array from ascending, from lowest to highest, we could do so using this. NP sort the array. Okay. We could also sort along different axes. So NP sort axis is equal to 1. We could sort each row. And then axis is equal to 0. We could sort each column. Sorted row-wise, it'd be 1, 3, 4, 2, 5, 9, 6. This 7 would go here, 8. Okay. Sorted column-wise, it would be 3, 1, 2, 5, 8, 4, and 6, 9, 7. So going back to the sorted column-wise, let me just make a quick point. You have to compare element by element, okay? So the first element, 3, 5, and 6, that's in correct order, okay? 1, 9, and 8 are not. 8 should be ahead of 9, right? So we get 1, 8, 9, and then 4, 2, 7 is not in correct order. 2 should be first, 4 should be second, and then 7 should be third. And that's what we get, 2, 4, 7. Okay. So that's how you would sort along different axes, okay? Now going to arg sort, which is basically we're sorting by index, okay? So we've got 3, 1, 4, 1, 5, 9. We create this array. We sort it, okay? So what exactly is the indices of sorted elements? Okay, this is the indices, okay, where it's sorted. It's 1, 3, 6, 0, 2, 4, 5. Okay. So let's look at this. We see that the index value after the sort is 1. And then we look at this element 3, which is 0. This is 1. This is 2. This is 3. Okay, so I'm talking about index values here. This is 4. This is 5. This is 6. Okay, so when we look at this, it makes sense. The first 3 values, okay, this is an index value of 1. This is an index value of 3. And this is an index value of 6, which it corresponds to. Okay, and that's 1, 1, and 2. Okay. So that's the way to look at it. It's by looking at the index and then taking, okay, using the original data set and then subsetting it by the indexed values. Okay. So we got this array and then we subset it and then we get the original values back. Okay, so if you count this up, basically you're going to have all the elements here, but in the correct order. Now let's look at something like this: banana, apple, cherry, blueberry. There's 0, 1, 2, 3. These are obviously text values, strings. And we could sort them by name, and then we'll get banana, apple, cherry, blueberry. Okay, if we sort it. Okay, but then we sort the indices and then we get the names. Okay, and this is going to be alphabetical order. So we get apple, banana. We will look at if two strings, okay, have the same starting letter, we would look at the next letter. And we see A goes ahead of L. Okay, and then obviously C cherry. So this arg sort recognizes alphabetical order with string values. Okay, so I want to make that point. And we see it's one, the sorted indices is 1, 0, 3, 2, which is apple, banana, blueberry, and cherry. Okay. Now we're going to continue with some more common vectorized operations and some statistical operations. So here we've got an array. We take the mean of this array, the min and the max. Okay. So obviously, like looking at this, it's pretty easy to tell what's the min, which is 5, and then the max, which is 30. And that's what these functions would give. If we're looking for the standard deviation, we would use this, and it's 9.27. Here we're going to sum along the axes of 0 and then 1, sum along the columns, and then sum along the rows. So 5, 7, 9 is if we sum along the columns, which we would add 1 plus 4, 2 plus 5, 3 plus 6. And then here we're summing along the rows, which is 6 and 15. Here's arg max and arg min. These commands tell you where the indices, where the maximum and minimum values are. So if I go np argmax of this array here, it'll return an index of 3, which is 0, 1, 2, 3, which is 30, which is correct. And then the argmin of this array is going to be 2, which is 5, 0, 1, 2. Now, if we have this 2D array and we do the matrix axis is equal to 1, where we find the max along each row, we're going to find that it's 1, which is 50, 0, 1, and then 0, which is 60. Okay. Now, if we want to find the min indices, right, along the columns, we would say it's looking at it from in column wise. We would say it's 0. 10 is the minimum of between 10 and 60. 20 is the minimum between 50 and 20, which is 1. 30 is the minimum between 30 and 40, which is 0. Okay. Here's another example. If we find the arg min, right, along axis is equal to 0, okay, we would find it to be 1, 1, and 2. how would we look at that? We would look at it column-wise, okay? So 0, 1, 2, 0, 1, 2, 0, 1, 2. This is obviously the min of this, 794, okay? This is using axis is equal to 0. Now we're going to be talking about universal functions, which are basically mathematical functions. Okay, so here we take an exponential of each element, okay? And then we'd also take the log of each element. And you can see the results here. Now we take the power is NP power. And by the way, this is equivalent to star star 2. I don't know if you recall that, but here's the square root. Here's adding and subtracting. So we're adding 5, 7, 9, and the same thing as we saw earlier. -3, -3, -3. This makes it more explicit. I mean, you're not going to make mistakes by putting this in, I guess, you know. Multiply x, y, and then dividing. Now on to performance optimization. I want to show basically the difference, okay, between a for loop and a vectorized operation. So we've been looking at these vectorized operations pretty closely, where we add, we multiply, or whatnot. Here I embed this time function here, time.time, right? I'm generating some random arrays first, okay? The array size is 10 to the 6, which is, I think, like in the millions, okay? And then we basically use a loop where we add each element, okay? A plus B, we time it. We time the time, end time minus start time. We do the same for the vectorized operation, okay? And you could see that when we run it, that the vectorized operation is 82.93 times faster, okay? This is pretty significant because when you write a lot of code, you're going to want it as short of time, processing time as possible, okay? I mean, this has implications in cloud costs and just you saving time in general. Okay, if you're running things in the cloud, for example, you're going to want to vectorize as much as you can because you want to save money, right? So that's the importance. Time complexity, it's important to understand this in the context of programming. You know, in our case, both NumPy vectorization and for loops, as you saw, um, it's ON. But I mean, you could see within ON, it's much faster, right? The vectorized. But here's a general guideline. O1 is basically the most efficient. O log n is very efficient, but not as efficient as O1. ON, linear time, which is what we saw, sufficient but scalable, still reasonable. ON squared, as you can see, it just gets worse, okay? We go ON squared is slow, ON cubed is very slow, O2 is practically infeasible, and ON factorial is the worst. And we could see this here. I mean, like basically this ON2 is basically the worst, right? This is constant in terms of time, and it just gets progressively worse. So this is useful for coding in general to be aware of these terms. Like I said, like I was mentioning earlier, you want your programming to be as efficient as possible. We're not just thinking in terms of like how nice and clear our syntax is written, but we're also concerned with how fast the computer programs actually run. Hey guys, so linear algebra with NumPy. We're going to be talking about some of the major concepts. Linear algebra is really important in understanding basically the underworkings of machine learning, deep learning, large language models. It's foundational to understanding these major ideas. Okay, we're going to start off talking about the identity matrix. Okay, so the identity matrix is basically a matrix with ones on the diagonals, as you can see here. Okay. And every time you multiply an identity matrix with just like a normal matrix, you should get back the normal matrix. I mean, the matrix that is represented by a square matrix. Okay. The function that we use to get the identity matrix is np.i. Okay. So if I do this, you see that we've got these ones on the diagonals. We're going to be talking about a dot product now. And basically, we're multiplying two matrices, okay? And what we're multiplying by is, okay, so does it, okay, so it does 1, 2 by 5, 7. And we're multiplying 1 times 5, and then we're adding 2 times 7. And then we're going to get that first term, which is 19, okay? Um, I could do the second one. Okay, so the second one, the second element here is 3 times 4. I mean, 3, 4. Okay, and 5, 7 to get the second element. Okay, so it's 3 times 4, 3 times 5, 4 times 7, and we get 43. Okay, now in order to get these two, we would do 1 times 2 times 6 times 8, and 3, 4, 6, 8 to get this bottom one. Now we could use this, obviously, it's a lot easier to use it, use Python. This gets a little messy here. Clean that up. And we could do that, put it in arrays and multiply it out, we'll get the same thing. Here we have something called solving for a system of linear equations. Basically, we've got this A, right? The original equation is this. It's A x is equal to B. Now we know what this is, A, and we know what B is. So we're solving for X. And when we do this for 2, 3, 1, 4, and then 5, 6, if we run this, we get 0.4 and 1.4. Now this is useful, I mean, especially if it's larger, right? I mean, like if we look at a simple example, we could be like, oh, what's the utility? We could do this algebraically by hand. But if it gets larger, then solving for x is a lot more complicated, right? So this does this, it takes care of that nicely. Now, taking an inverse of a matrix, we take the inverse of a matrix A is A minus 1, such that A times A minus 1 is an identity matrix. Okay, and a matrix is invertible only if the determinant is non-zero. Now here we have a case where it determinant is greater than 0, and we're going to get that, an inverse, okay? So if we multiply this matrix by 2, 3, 1, 4, okay, we should get the identity matrix. And if we do that, no, what did I? Yeah, 1 second. Okay, so what I should have done is the NP dot and not multiply that out. That's an important point. So this is a dot, not multiplying, okay? NP dot A times A inverse, we should get the identity matrix, which we do. We get the ones, and this is a negligible value. Basically, it's 0, okay? Moving on to determinants. So like I was mentioning, if the determinant is not equal to 0, then the matrix is invertible. If it's equal to 0, it's not invertible. So if we take the determinant of this matrix here, which is just multiplying out the rows and columns, we get 5. Finding eigenvalues and eigenvectors, we can do so by doing this. np.linearalgebra.eigenvalue. Okay. And we find that the eigenvalues are 1 and 5, and the eigenvectors is 0.94, 8683, and 0.31. So the eigenvectors should be read this way, right? 0.93 and 0.13, the first columns, okay? That's would be considered an eigenvalue, the first columns of the rows, okay? Here we could do something like where we calculate a covariance matrix, and the columns could represent features or variables. And it's useful to compare variables, say in a model, to see if they're related or not, right? If they have a perfect relation, the perfect correlation of 1, basically it could be redundant information. Okay, so here we take the np.cov, row var is equal to false, right? Because we're looking at it column-wise. Row variance, we don't care about. And then we get 0.938, 0.853. These are the covariances, and these are the variances, okay? We could use what we just learned previously to model a linear regression. And this is common where we would find the beta variable, right, which is the regression coefficient, where we get x transpose times x. We take the inverse of all of that, and then we multiply that by the x transpose and then the y vector, okay? So here you could see the x, right? We've got 4 rows, 2 columns, okay? And then we've got 4, an array of 4, a 1D array of 4 values, okay? Now I showed you the inverse. What we do is we do xt ampersand x, right? And then times xt times y, okay? The important thing to note is the dimensions, okay? So if I look here below, let's do a little bit of this. So I'm going to run this first. Let me just run this first. X shape is 4, 2, right? X T dot, I wonder if I could do this. Oh, wait. Yeah, it's 2, 4. Okay. And then what's the Y shape? It's a 4. So let's look at this inside term, X transpose multiplied by X. Okay. We have 2 by 4 times 4 by 2. Do you see that? So what I'm saying is it's 2 by a 2 by 4 matrix and a 4 by 2. It's important that these two are equal in order for the multiplication to occur. Then you've got a 2 by 2, right? And then you're multiplying by another transpose here, which is a 2 by 4. And these twos are equal here. So you got this 2 by 4. And then finally, you're multiplying it by the y, okay? Which is a 4, okay? So I want to make that clear, okay? And then you're going to end up with a 2 values, which you get here in the regression coefficients. Regression is fundamental to machine learning. It's pretty foundational. Um, there are higher order functions that have been created by like scikit-learn and stats models that do all of this for you. But it's good to see kind of the machinery behind these models. Principal components analysis is another important tool in machine learning. And basically what we're doing, like with this array, is we're taking the mean, right? We take it's the centered value. We take the second step is the covariance matrix. Third step is taking the eigenvalues and getting the eigenvectors. Then we arc sort, if you recall, in descending order from highest to lowest. Okay. Then we get the eigenvectors based on that index, and we get the eigenvalues based on the index. Then we transform. We do a dot product on the centered variables times the eigenvectors to get the principal components. Okay. And here's the principal components. That's it. This is important in the sense that, like, basically, if you have like multiple variables, like say if you have 100, 200 variables, we could reduce it to 3. But those 3 will contain most of the information for that 100. Okay. Here we've got 2 features, okay, each column, obviously, and this is a very simplified example, but if we were to work with 100 features, we could reduce it to 3 components. Okay, so that explained most of the data. So that's the importance of that. So on to sequences, we're going to be talking about A-range and NP-lin space. These are useful for graphing, also for machine learning, right? Like finding the optimal value. Like you could lay out a sequence of values, say like 1 to 10 or something like that, and which one basically optimizes a machine learning model, right? What makes it generalize well on the test set. So here we create an array from 0 to 20 with a step of 2. So we got 0 to 4, all the way up to 18. Remember this 20 here It's basically not included. Okay, so I mean, like if you got like this two-step here, it'll go up to 18. Okay. And here we get NP linspace. We create 10 evenly divided space numbers between 0 and 20. And it goes up to 0 to 20, and it's evenly spaced from 2.22, 4.44, right? So the key differences. Okay, so the key differences, let me just clean this up here, is NPA range creates an array with a fixed step size, right? So every two values it skips. And then NP linspace creates a fixed number of values between 2 points. Okay. We're going to be talking about random number generation. Now, this is useful for things like creating synthetic data sets, okay? Performing experiments, having data sets that you could test some models on with randomly generated data when you don't have enough data or you don't have the type of data you want. You can create these things called synthetic data sets, okay, that are useful. Here is a uniform random distribution where we create 5 random values between 0 and 1. Here's a standard normal distribution, okay? Here are some random integers, like 5 random integers between 1 and 100. Here's a random shuffling. So here we replace is equal to false, meaning that we don't um, replace it. So once we draw it out, it doesn't come back in. Here's a permutation. This is just basically randomly shuffling the array. Here is a good important concept of basically reproducing results. Now, sometimes you're going to work with a data set and you're going to want to keep it fixed, this randomized data set, okay? And that's for, say, for example, model comparison, right? You're not going to want to randomize, you're going to want to randomize a data set, for example, and then keep it fixed and compare, like, say, two models, like a linear regression and some other model, like a random forest or decision tree, whatever. And you want to compare the results against that. Now, if you randomize the data sets twice, basically the results could be inconsistent, right? If you randomize the data set for linear regression, and then you randomize the data set for random forest, the results are going to be different, not maybe because of the model, but because the data is different. Okay, so that's the point I want to make. This np random.seed keeps it fixed. So if you look at this, it's 113, whatever the sequence, but it's going to be the same. Each time I run it, it's not going to change, right? So that's the idea of the random seed. And here I'm replacing it's true, so I could replace it. It'll the same value could show up. Okay. So I showed the unit statistical distributions here. Here's a uniform distribution where we roll a dice 1 to 6, and they're all equally likely. Okay. But of course, it's randomized. It's 1,000. I mean, there could be some differences at times, but 1 to 6, they all have an equally likely chance of rolling. If we roll it 1,000 times for each, of course, there's going to be some variation. Here's a normal distribution with a mean of 50 and a scale of 10. Here in NumPy, it's important to note that they're going to use these things called location and scale. And that's basically, in the normal case, it's mean and scale is standard deviation. And it's going to be like 5 values. Okay. Here's a binomial where we have 10 number of trials. The probability is 5 and the size is 5. Okay, so 5 samples from 10 flips of a fair coin. So the way to interpret this is that each number represents how many times heads occur in 10 flips. Okay, so for the first trial, we got 5 heads out of 10. In the second trial, we got 6, and so on. In this case, we got 3, we got 8. So it's the first 2. I should have put a random seed so that I fixed this trial so that the results were consistent. But in the first trial, we get 3, and then the second trial, we get 8. Here's a Poisson with the lambda is equal to 3 and size is equal to 5. And interpretation is this. In the first hour, we get X0 customers arrived. So we get 1 customer arrived. In the second hour, we get 1. In the third hour, we get 3 customers arrived, right? The average arrival rate is 3, okay? And we could get values like 6, for example, 6 people arrive. But in average, the arrival rate should be 3. Now to put these things in perspective, okay, like there's a cold start problem I'm giving here. And say, for example, McDonald's wants to see how a potential product will do, right? So different flavor of McFlurry, Rocky Road. I know that there's cookies and cream, but they want to try a different ice cream, Rocky Road. So they don't have data on that. They could generate the data via products that like that they have based on the Oreo McFlurry. Okay, so they've got data on the Oreo McFlurry. Now, how can we use that data to generate data on Rocky Road and see how that does? Okay, so what we could do is basically take the mean of the Oreo McFlurry and the standard deviation of that historical data and generate um, a data set based on that. And we generate like 90 values, right, for the months of June and August. And then we simulate a weekend effect, right, where we say that there's going to be higher sales on the weekend and we bump it up a little bit. Okay, so we give like some kind of weekend boost, and that's based on a random uniform. And if I do that, I've got some type of data set that I could work with based on using the characteristics of an Oreo McFlurry. Okay, so it's got a mean sales of 500 and a standard deviation of 100. Okay, so that's the idea of what a synthetic data set would be useful for. Like where we have this cold start problem, we want to see how a product will do, but we don't have the data on it. What we can do is take something similar to it and take their historical data and model it off of the parameters of their historical data. In this case, the mean and the standard deviation. So in data analysis, it's pretty inevitable that you're going to be working with missing data, and NumPy supplies some useful functions for that. So here's a simple array, I mean, with some NANs. And we could use this is NAN data to kind of use it as a Boolean to see whether it's true or false, okay? I mean, this is useful in conjunction with other functions. So like we could count these up and say how many of them are missing, and we could do things like that, like aggregate it up or whatnot. But for this simple function, it's is NAN. Um, that's the function, and it's useful for creating Booleans based on that. Now, if we wanted to remove these missing values, we could use this negate Boolean mask, which is this thing here. And we do data that we subset it by this is NAN data, right? And then we get the clean data set, which is 1, 2, 4, 5. And you could see that all of these are dropped. We could also replace it with a specific value. In this case, like for example, the mean. If we want to get the mean without worrying about these NANs, we could do this .NAN mean function, and it'll take the average and ignore the NAN values. Okay, you wouldn't be able to do that with a regular mean function. And then we basically replace that. Okay, so that's what we do with this np.nan to num data. NAN is equal to mean value. Okay. This also NaN max will ignore the mean val in the NaN values, and you could do the same thing for min. Now here is something pretty useful where we have to interpolate data. We could do this based on like a linear trend, or we could do this based on mean, like which we saw earlier, or there's some more complex functions that we could use. But in this case, I'll show you kind of like a simple example here. Okay, so what we're going to do is create indices range with the length of the data. We're going to create a mask, which we saw earlier. Okay, and then we're going to interpolate the missing values where we use the indices, the mask that we used, right? The indices, and then the negation mask, and then the data mask, right? And then we're going to get 1, 2, 3, 4, 5, 5. Okay, so explaining the code basically fills in the missing values, right? An array using linear interpolation. It creates an array with missing values, right? That's what we did on the first. And then we create an array of indices, okay? So this is the position of the elements like we were mentioning, I mentioned earlier, right? It always starts with 0. Then we identify the missing values, okay? Where it's a Boolean, true or false based on whether or not it's missing or not. And then we perform a linear interpolation. So the line data mask is equal to NP. Interpolation, okay? Indices mask, and then the data mask fills the missing values. So the indices mask gets the positions of the missing values. The indices swirly sign mask gets the positions of the non-missing values, right? And then the data mask gets the actual non-missing values, okay? And then this interp function uses those non-missing values, right, to calculate what the missing values should be based on the straight line linear interpolation between the surrounding known values. So that's what we get. 1, 2, 3, 4, 5. You could see that basically it reads the 3 in based on the 2 and 4 values, okay? And then 5, it reads in 5, right? If it saw another value here, maybe like a 6, it will read something else in. Or 7, it would read in a 6. Building graphs with NumPy. NumPy is really useful in conjunction with matplotlib. So in something like this, we could use NP linspace from 0 to 100, steps of 10, basically, to create like a sine curve here. Okay. A histogram also we could use. Not NP linspace, but basically we could use the random number generation that we saw earlier and then just plot hist, which is a matplotlib function. Again, just recall that NP random seed will fix this, but you see without the NP random seed, the distribution changes, okay? It's normal, but there's gonna be some slight variation, just to point that out. Here we use the NPA range, okay, for a bar chart. And we could see A, B, C, D, the values. NP mesh grid is a very useful function. It's a NumPy function used to create a grid of coordinates from two 1D arrays. And it's typically for 3D surface plots or vector field visualizations. Now that's useful for things like gradient descent optimizations. You can see it from a 3D angle, okay? But here's a simple curve. It's x squared plus y squared is equal to z. And you can see it's a quadratic loss function, gradient descent, where there's like a global minimum. Okay, and global minimums, as you know, is useful. Like we don't want to get caught in local minimums or whatnot. A global minimum is an optimization in the true sense of the word. Okay, for machine learning in any case. Now there are more machine learning and data science applications that NumPy is extremely helpful for. So I'll give you an example here. It's NP clip. And this prevents extreme outliers. Okay, so if I do NP clip data 10,500, it'll restrict, I mean 10, 100, I'm sorry. It'll restrict the range to 100, okay? And you see that 500 and 1000 is basically clipped out. So even 100, I mean, yeah, 100 is replaced by 100, okay? Now that's useful for outliers, okay? If we have outliers influencing our data set and we don't want that influence on it, we can get rid of it using this NP clip function. Gradient clipping is also used in deep learning. Okay, so in neural networks, exploding gradients can cause instability in training, right? So NP clip is used to limit the gradient values during backpropagation. Say, for example, these are the gradients. We want to restrict it to -5, 5, that range. We could do so. Another thing a useful thing for NP-clip is basically mathematical operations like logarithms require positive values. And division by small values can cause instability. Okay. So we could limit it and reduce the values, right, to the range that we're interested in, the smaller range. I mean, if you see that basically -1, if you take the log of -1, it's going to return an NaN, invalid value. Okay. And this is more common than you think. In time series modeling, if you take the difference, you can end up getting something like a -1, and you want to apply an algorithm, your algorithm will stop. And if it's a large data set, it's a real pain because it could take an hour and 2 hours and it finds this value and it just completely halts it. So this clip value, this clip is helpful in the sense that it'll prevent that from happening. Okay, on a large data sets. On small data sets, you won't see the value in small data sets, but in larger data sets, you will. And then finally, we could use NP linspace to find the optimal parameter value so that the model neither underfits or underfits. And we saw this NP linspace before. We find a range from 0.01 to 1, evenly 10 space values. Okay, and we run a ridge regression using grid search. So that NP linspace, this NumPy function is extremely useful because we're going to go through a range of these values, okay, on subsets of the data using cross-validation, 5 cross-validation folds. And then based on the R squared, we could find the optimal value. And the optimal value is 0.01. Okay. This is commonly used in machine learning in conjunction with scikit-learn, and it's very useful for finding these optimal parameters to optimize your model, to make the model either to prevent it from either underfitting or overfitting. So that's the end of the course. Thank you very much. I hope you learned a lot, and I hope to talk to you soon.